Hi guys, and welcome back to my channel. In this video we're going to be talking about molecular motion, specifically molecules in the gas phase. So we're going to be talking about sort of properties of the motion of gas particles, and at the very end we'll discuss the kinetic molecular theory, which is sort of like all of these experimental observations combined into one powerful theory, and we can use this theory to sort of define the key properties of an ideal gas. So this defines sort of the key properties of an ideal gas, and then we can go and use this theory and actually get some pretty cool implications, like the root mean squared speed of an ideal gas at a certain temperature and other sort of things that we'll show in future videos. Okay, so first I just want to talk about some properties of molecular motion of gas particles, and the two really important properties that you should know are diffusion and effusion, right? And they sound really similar, so it's easy to get them confused, but hopefully with this video I'll define both the terms and give you some key examples to think about so you can differentiate between the two. So what is diffusion? Diffusion is the gradual dispersal of one substance through another substance. So that sounds kind of vague. Let's think about an actual example, right? So the key example I like to think about is if you spray perfume at one end of the room, eventually you can smell it at the other end of the room, right? So if I have a big room and there's some gas particles here which resemble the perfume smell, right? That means eventually these gas particles will sort of disperse throughout the entire volume, and you can and you'll find the gas particles at the other end of the room, which means that you can smell the gas at the other end of the room, right? So basically the example is if I spray perfume at one end of the room, the gas particles are going to spread out to take the entire sort of volume of the container they're in, and then once they spread out, you can smell the perfume at another end of the room. And that is what diffusion is. The next key property is effusion. This sounds really similar, but it's very different. Effusion is the escape of gas through a small hole into a vacuum, right? So one example of effusion, which technically isn't effusion because we're not escaping into a vacuum, but the pressure difference is really large, so we can sort of approximate it as the outside is a vacuum and the inside is the gas, right? If we think about gas leaving a punctured bike tire, so say we have a tire and there's sort of like a tiny pinhole, right, in the tire. The gas inside is super pressured. There's lots of gas. That's why you have a high tire pressure. And then you puncture this and the gas can escape through the hole, right? And basically the outside is so low pressure compared to the inside of the bike tire that you can still treat it as an example of effusion, because it's essentially like the gas is moving from a pressured area into a vacuum. Even though the outside isn't a vacuum, it's at atmospheric pressure. The pressure is so low in comparison that you can treat it sort of like effusion. So these are the two examples I go back to when I'm thinking about diffusion and effusion. Diffusion is when you sort of disperse, the gas particles can disperse through an entire medium, such as the perfume. And effusion is when you puncture a tiny hole and gas particles escape into a vacuum. Okay, so now let's talk about Graham's law of effusion. So this is an important law that you might have touched on in AP Chem. I don't know. It's sort of barely covered, so we'll talk about it now. Graham's law just states that the rate of effusion is proportional to 1 over the square root of m, or the rate of effusion is inversely proportional to the molar mass, the square root of the molar mass. And what does that mean, right? This means that heavier molecules, right? Heavier molecules, what does that mean? Heavier molecules implies that your molar mass is large, right? And heavier molecules with large molar masses will move slower because the rate of effusion is proportional to 1 over the square root of m. So the larger the molar mass, the slower the rate of effusion. And this makes sort of intuitive sense because heavier molecules will have sort of more inertia, right? They won't want to move as much because they're heavier, and then they'll be more resistant to movement. so they'll effuse slower, right? And we also know that the average speed is proportional to the rate of effusion, because you can think about this like if you have heavier molecules sort of escaping a bike tire and they move slower because they effuse slower, that sort of means that the speed of the heavier molecules are slower because they're effusing slower, right? You can sort of relate these to effusion and the speed at which they're escaping pretty easily. That means the average speed is proportional to the rate of effusion, and therefore the average speed is proportional to 1 over root m, because the rate of effusion is proportional to 1 over root m as well. So this is sort of just a key point to note, because these observations about the average speed will come back when we derive the formula for the root mean squared speed of an ideal gas in a future video. Okay, so now let's look at some sort of examples of where you would use rate of effusions, right? Generally, we don't care about the actual rate of effusions. We care about the relative rates of effusion of two molecules. And this is where we like to use ratios, right? Whenever we're talking about relative, we like ratios. So if we wanted to look at the relative rate of effusion of a molecule A versus the molecule B, we know that each rate of effusion is proportional to molar mass by some, it's some constant that's the same divided by the molar mass, the square root of the molar mass. So the constants will sort of cancel out, and we just get 1 over the square root of molar mass of A divided by 1 over square root of molar mass of B. And we can simplify that to get this sort of square root, where we have that the rate of effusion of A over the rate of effusion of B is equal to the square root of molar mass of B divided by molar mass of A. So you can see that the molar masses and the rate of effusions are flipped, right? The A is on the numerator for rate of effusion, molar mass of A is on the denominator for rate of effusion. And that sort of makes sense, because let's think of an example. Say we have the rate of effusion of, or A is a much smaller molecule than B, right? Molar mass of A is much smaller than molar mass of B. What does that mean, right? That means that the rate of effusion of A should be much faster, right? Rate of effusion of A should be much faster than rate of B because it's smaller. And we can see that when we plug that into our expression. We have molar mass of B being much greater than molar mass of A. We get a really high positive number, which means that the rate of effusion of A is much greater than the rate of effusion of B. So you can sort of intuitively see why our A and B should be switched or flipped. And we can also look at the time of effusion, right? Time of effusion is just inversely proportional to rate of effusion, because rate equals distance over time, right? And if distance is sort of a constant, we have that rate is proportional to 1 over time, or time is proportional to 1 over the rate. So we can do the same thing. The time of effusion of molecule A over time of effusion of molecule B, that's going to be 1 over the ratio of the rate of effusions. So we just flip this square root, and we get square root molar mass of A over molar mass of B. Okay, so these are just some examples of where you would use these ratios in order to conduct some analysis and look at the relative rates or relative times of effusions of two different compounds. Let's look at sort of a USNCO question that touches on this idea of rate of effusions. So cotton balls are soaked in concentrated solutions of HBr and a methylamine and are placed at the same time in opposite ends of a glass tube. What is observed? So let's sort of draw a picture. We have a glass tube. We have cotton ball with one, cotton ball with the other. And say this one has CH3 NH2 and HBr. So first of all, what is going to happen is these two are going to come and meet and react, right? That's what is essentially happening here. There's a reaction between our methylamine and our HBr. What reaction is this? You can tell that an amine, right, is going to be basic because the amine has a lone pair on the nitrogen, so the nitrogen can sort of pluck a hydrogen, a proton, because it has a lone pair. So your methylamine is basic, HBr is obviously acidic, So we're going to have an acid-base reaction. And this is going to meet somewhere in the middle, and the NH2 group is going to attack the hydrogen, right? And we're going to form CH3NH3 plus, we form a salt, and Br minus, right? Basically, this base is going to abstract a proton from the HBr. This is just like any other acid-base reaction you might have looked at, right? So, based purely on that, we know that there's going to be this CH3NH3 plus, Br minus salt that's formed, in this reaction. So we can look at C and D, right? And we see that it's saying that a white ring of NH4 ammonium bromide is going to be formed, right? Both of these options have ammonium bromide being formed. We know that's wrong because that doesn't make any sense. This is just an acid-base reaction. This is our base. This is our acid. We abstract a proton, right? So we can immediately eliminate C and D. Now let's look at A, right? How does this process actually, happen? This process happens because when we soak these cotton balls in our concentrated solution, the actual compounds are going to effuse through the air, right? Say we soak this in methylamine. Eventually, this methylamine is going to evaporate into the air, and it's going to move around because it doesn't want to stay in it doesn't want to all bunch up in one place, right? The particles are going to effuse through the tube and fill the volume, right? So what is the methylamine going to do? It's going to move through the tube, and it's all concentrated on the left side, so it's going to effuse to the right side. And same with the HBr, right? The HBr is going to effuse to the left side. So we're going to have these particles sort of drifting through the air, and eventually once they meet, right? Once the particles meet, they can actually react, right? We can't have them reacting before they meet. So how are we going to decide, what is the difference between A and B? Let's first look at that. In both of them, we have the compound that we know will form, right? This CH3NH3Br. But the two options, one says it's going to form in the tube closer to the side with the HBr, and the other one says closer to the side with the CH3NH2. So basically, the question is, where are these going to meet? Where are the particles going to meet? Are they going to meet closer to the methylamine or closer to the HBr? And how do we figure that out? Let's look at the rate of effusion, right? Let's look at the rates of effusion. So let's look at the molar masses, right? Because we know the molar mass affects the rate of effusion. That's what we were just talking about here. What is the molar mass of HBr? We know the molar mass of HBr is greater than the molar mass of methylamine. You can do this calculation, right? Molar mass of HBr greater than molar mass of methylamine. That essentially means that the HBr is heavier than the methylamine, right? So the HBr is going to effuse slower through the air. And when we have HBr effusing slower through the air, that means that when the reaction actually takes place, the CH3, the methylamine, they're going to meet closer to the HBr, right? Because given the same amount of time, this methylamine can move farther than the HBr moves. So that essentially just means that the particles are going to meet closer to the HBr because it's heavier and will move slower. So the correct answer is A. A white ring of CH3NH3Br forms in the tube closer to the side with the HBr. Okay, so this is just an example of a question you could get on, where you have to use your knowledge of rates of effusion. And it's pretty simple. You just think the heavier molecule is going to move slower. So where are they going to meet? They're going to meet closer to the heavier molecule. Okay, now let's talk about effusion rate and temperature dependence, right? We just talked about effusion rate and molar mass dependence. Now let's look at temperature dependence. So experimentally, we find that the rate of effusion at temperature 2 divided by the rate of effusion at temperature 1 is equal to the square root of T2 over T1. And what does this tell us? This tells us that, say, at a higher temperature, right, raise the temperature, that means that our rate of effusions are going to go up, right? And that makes sense. If I raise the temperature, there's sort of a more fast motion, right? Because raising the temperature means I raise the kinetic energy of the particles, and that means they're going to spread out faster. They're going to effuse faster. And since rate of effusion is proportional to the average speed, we know that the average speed is proportional to square root t, right? That's just found from this expression. Average speed is proportional to square root t. And if we combine the relationship we found before, if you remember from a previous slide, we talked about how the average speed is proportional to this 1 over the square root of the molar mass. And now we know that it's proportional to temperature, or square root of temperature as well. We get that the average speed is proportional to the square root of t over m. And this should look like awfully similar to the root mean squared speed you've sort of seen in AP Chem and we'll discuss in another video, right? We know from AP Chem, we know that the root mean squared speed, VRMS, is equal to square root 3RT over m. And you can see that if I sort of change this a little bit, I get square root of 3r times square root of t over m. So we can see directly this sort of proportionality that's happening, right? This VRMS is equal to some constant, which is root 3r, times my square root t over m. Okay, and now finally I want to talk about the kinetic model of ideal gases. This is sort of what everything builds up to, and this model sort of tells us everything we need to know about an ideal gas, and we can actually use this model itself, this kinetic molecular theory, to derive the formula for the RMS speed of ideal gas molecules, and this is done in another one of my videos, right? And as I said in the last slide, VRMS is square root 3RT over m, and just using this model, right? Just using these 4 points, these 4 key points, we can derive this from first principles, which is, really cool. So let's talk about these 4 points, right? The first point is a gas consists of a collection of molecules in continuous random motion. So what does this mean? Continuous random motion. That means that random is the most important thing here. No one direction is preferred, right? So this is a key assumption we use in the derivation, is that the preference to move in the x direction is the same as the preference to move in the y direction, is the same as the preference to move in the z direction. So basically all 3 directions are equivalent, right? That's essentially what this first point means, and it's really important to the derivation. The second point is that gas molecules are infinitesimally small points, which means that the molecules themselves have 0 volume. And one way to think about this is that if I look at one molecule, one tiny gas particle, right? And there might be a bunch of other gas particles in this gas sample, but what this gas particle sees is basically the entire volume of the container given that one gas particle. So if we want to account for these things having volume, a non-zero volume, that means each gas particle is not going to have the entire volume of the container to go into, right? Each gas particle is going to have the entire volume of the container minus the volume of all the other gas particles added up, right? Because one gas particle cannot go on top, into the same position as another gas particle. But in the kinetic molecular theory, we assume that every molecule has 0 volume, which means that if I zoom in on one gas particle, like if I have a sample of gas, I look at the motion of one gas particle, it acts as if the entire volume is for itself, right? So hopefully that assumption makes a little bit of sense. The next point is that the molecules move in straight lines until they collide. And that just means, right, there's no sort of forces on the gas particles. They're just going to move in straight lines, with constant velocity until there's a collision and they change direction, right? But they move in straight lines, which means that there's no sort of forces acting on these gas particles. And that sort of brings us to the fourth point, the molecules do not influence one another except during collisions, right? Do not influence one another except during collisions. And what does that mean? That means there's no attractive or repulsive forces apart from collisions. So we assume that there are no intermolecular forces, no IMFs. So this just means that, this is a really important assumption that we use, is that if I zoom in on one gas particle, and even though, right, there might be thousands and thousands and thousands of other gas particles around it, it basically acts just like it was the only gas particle in that space, because it doesn't know of any other particles' existences, because there's no forces between them, right? So that's a really important assumption that we use, is that if I have this sort of container with a bunch of gas particles, and I zoom in on one, how that one particle acts, it doesn't matter if there was a billion other gas particles around it or no gas particles around it, because there's no intermolecular forces, or this is the assumption that we make, is that there's no intermolecular forces. So we can sort of simplify this problem. Instead of dealing with, the fact that there are billions of particles around it, we basically say, oh, there's no particles around it. We can just think of the massive system as just basically a one particle system, because there are no interactions. So that's how we use that assumption. And these are all assumptions, right? That's a key thing to note, is that none of these things are true, right? Gases do have intermolecular forces, right? Everything has intermolecular forces. Gases do have volume themselves. The gas particles do have volume themselves. And they might not move in continuous random motion there because there's forces between them and all these sort of things. But these are assumptions we can make to simplify our problem, because they're basically true for most gases. And that's why we call, these are the rules for ideal gases, right? Which we're assuming ideality. We're assuming like the most ideal sort of conditions, that there's no intermolecular forces, there's zero volume, all of these sort of things. Okay, so this is basically all I wanted to talk about in this video. I hope you guys learned something. Thank you guys so much for watching, and I'll see you in the next one.